Hello, everyone. Welcome back to our research seminars, RAS. I'm very glad to have João Moreira with us today. He's a former student from our lab, and he's currently working at Intel in Portland, doing some work in security. And João is going to talk a little bit to us today about his state of kernel control flow integrity. João, thank you for the lecture, and the floor is yours.
Okay, thank you, Sandro. It's really a pleasure for me to be talking to folks at Unicamp. I keep the university and the institute in special like deep in my heart. I miss those days a lot. So it's a little bit like nostalgic to me to be talking to you all. Thank you for having me. So the topic I'm going to talk about today is like control integrity, which especially specifically in the Linux kernel, which is specifically something I researched throughout my PhD days in Unicamp. But at the time, I mean, we were not like so lucky about it because there were like a lot of things going on at the same time. But eventually, like things moved on, and now the kernel kind of like embraced control for integrity. And I'm here like to talk a little bit about how this happened, and I mean, more like the key research points that enabled it at a certain point and all that. So I have like some notices and disclaimers, which I have to tell you about. I don't need to read this, but be mindful of like all these things before you assume anything about the presentation. Um, and me, I'm João Moreira, like Sandra introduced me. Currently, I'm an offensive security researcher and a research manager at Intel Corporation. So I work like doing part technical work, part management work. I have like a small team of 4 people working with me right now, and I'm like part of like a bigger security team where we normally try to prevent bad things from coming to Intel products. So if there's like launch or if we're like working on new technology, how do we make like this technology better in terms of security? So it's like pretty much a research team, because we're not like trying to interact with product creation. You know, we're not like kind of holding new products from being launched or anything like that, but we're like working in parallel by just like taking a look and making sure that things are safe in that end. I have also like done some open source contributions in my time. I mostly work with a LLVM these days, so I do like a lot of open source contributions to LLVM, mostly on like how LLVM supports compiling the Linux kernel. That's again an experience I got when I was doing my PhD, so it was like kind of very meaningful for me to learn all the things I learned, and now I'm like able to do work like this. I also did some work on GCC, some work on Nmap, and also like some work in the kernel itself. Before coming to Intel, I worked a little bit with SUSE Linux, which is a Linux distribution. Probably heard about it. I was doing toolchain work there, mostly like working on live patching features. So it's like if you want to patch a process while it's running, sort of like patching the binary, you just go and patch the binary itself, well, the process itself, without like needing to turn it off or without like needing to kill the process and things like this. And before that, I was a PhD candidate at LSC, right, at Unica. And of course, not of course, but happily, I finished the PhD. So not anymore like a candidate and not also like a dropout either. So yeah, very happy to have spent those days there. And this PhD program is where like all this research started. So let's get to it. Here are some acronyms just in case you get this presentation later and want to like figure out what we're talking about. Before we go into control integrity, let's talk a little bit about like memory corruption, which is the problem we will try to handle here. So imagine you have like this function, and please don't mind my bad writing and all that. Imagine you have this function, which is like a function foo that gets like a pointer to a sharp buffer. And then you have like a local buffer in your function, which I call like buff, and it has like 3 positions. And then you run strcpy, which is like a string copy function that's going to copy something you got from outside the function into that specific buffer. And then you're going to return. I mean, this is like a pretty dummy function, but just to show you how this kind of thing will work. So basically, when you're like kind of running the string copy function, you're like basically taking the pointer from a buffer where the data is coming from, and like copying it to another point to the destination from another pointer you got like as an argument, the second argument. And when you do that, so look, mind the left side here now. It's like a stack, right? So in the stack you have like this uh, register activation record. So whenever like running a function, it has like a return address on the stack, and on top of this return address, you have like the local variables for that specific function you're running. So I'm assuming you're all like very familiar with this since you are in LSC. And so going back to strcpy, when you start running it, you start like copying from a buffer into another buffer, and you start like make kind of like overwriting the data, right, or the buffer into your local variables. And you do that until you find like a -0, right? So you need like a new byte to tell the strcpy function that you already like copied all the data. But if for some reason you get like a buffer that it's bigger, I mean the from buffer is bigger than the to buffer, well, basically this means that you're going to overwrite the entire buffer. strcpy is not going to find the -0 or the new byte, and it's going to like still copying. So that's the behavior of strcpy that it regularly does. And when you start like you continuously keep writing without like finding the new byte, you're going to override like all the local variables, and eventually like you're even like going to override the return address on the stack. And what this means in practice is that you can, for example, make this return address point anywhere, even the stack itself. And then in the stack, you can put like some evil code that does like some malicious things. So like, and here I'm talking like instructions, like encoded instructions, right? So encoded bytes. And when the return executes, instead of like returning to where it was supposed to return, so to the color of the function foo, it's actually like going to return into your stack and execute that evil code that the attacker passed through the C char buffer. So this is like an attack. It's like quite old. We have like many mitigations again this specific attack nowadays, but it's like a starting point for us. And this is what we call like kind of control flow hijacking attack, because the attacker was able to exploit like a bug in the way that memory is written to, and from there he was able like to hijack the control flow execution of the program by taking control of the address which was going to be used by the return instruction. Like I said, there are like a bunch of mitigations for this. The first one and most important is write XOR execute kind of policy. So right now, if you have like a running process in any operating system and you have like memory pages which are writable, what do you basically need to ensure that these pages are not going to be executable? So an attack like this, where you have like a stack is a place where you are keeping local variables, and it needs to be writable, right? Because you need to write to your variables. This means that the CPU, if the CPU ever tries to execute an information which is in these pages, the CPU is going to trap. It's not like going to allow you to execute this this specific data, which is in a writable page. So I mean, this is actually like implemented by the OS. I mean, the policy, not exactly by the CPU. But if the CPU tries to run a page which is not executable, it's going to trap, right? So basically, you rely on the OS for ensuring that this is not possible anymore. You're not like possible to write evil code somewhere in the form of a variable and then redirect control flow there. Something else which exists, it's not as effective, but it's also like useful, is ASLR, which is address space layout randomization. It's like a technique where also like handled by the OS. Whenever you have like a running process, like code snippets and variables, I mean, all the memory layout of the program is kind of like randomized. And because of that, an attacker trying to override like a pointer, he's not like going to be able to know where he needs to point to. So he's not going to be able to figure out the address in the buffer that he needs to point to in order to execute the code that he's executing, because all of this is randomized, and it makes like an attack much harder. Yet there are like new techniques to bypass this. One of these techniques is code reuse, which is basically instead of like injecting code that you wanna execute, you basically like already use something that is present in the process itself. So in many situations, it's possible to just I'm sorry, I had like an interruption here. Let me just close Teams. Okay, I'm sorry. So yeah, going back. Sometimes you just have like functions inside the program you're running, and these functions will like already uh, do something that, if executed out of context, will already like be sufficient to cause some damage or like enable a hacker to do something. So sometimes you don't even like really need to inject code and then jump to it in order to execute what you want to. So besides this technique, there's also like a memory layout disclosure attacks, which are like sometimes you are able to leak data from the memory layout in a way that allows you to figure out all the randomization that was done, and allow you to kind of figure out where the place you need to point to is. Sometimes people will even like use brute force to bypass ASLR and things like this. So these two mitigations did not like solve the problem entirely, although they helped. Uh, so now let's talk a little bit about a slightly different kind of problem, which is like more focused on what I'm gonna discuss here later in terms of like mitigation implementation and all, which is code pointer corruption. So first we saw an attack that was basically corrupting the return, and now we're going to see how it could be used to corrupt a function pointer, which is pretty much the same kind of principle, right? So you have like a function pointer inside the function foo. This function pointer at a certain point it gets like the address of the function bar, and then it runs a string copy, and then it invokes the function pointer. And in the function bar, you basically like have a user ID check, and if the user ID is not valid, uh, it's going to return. Otherwise, it's going to run a function that's called make me reach, which is basically the goal of the hacker to execute this function. So once you want to attack this, assume you have like this specific memory layout or stack frame for the function foo. It's like all your local variables are inside that green area. And in that green area, you have like a specific part where it holds the FPTR content. So FPTR has like the contents of, which are like the address of bar. So that's more or less like how your memory layout is when you start executing string copy. Like I said, FPTR is pointing to bar. And when you execute string copy, you start like copying things over your buffer, and that's cool. And eventually you overwrite the function pointer, and you can overwrite the address of bar inside the function pointer. And you can, for example, replace it by the address of bar plus an offset, which actually is going to execute the function make me reach directly. So when you were invoking FPTR, instead of like going to the beginning of the function, you are now going to the function you want to execute directly. So as you can see, I mean, we did not like really need to inject malicious code here to execute something that we might want to execute and that we're not supposed to. So like this is code reuse attack, or basically we are like reusing code, right, that is already present in the process, and we are like basically reusing legis instructions out of their original context. And it's kind of like very very hard to mitigate, right, because you don't want to like not allow certain functions or certain code snippets to be present in your code. Is not something that we can do, but instead, I mean, we can try to confine the indirect branches to save privately computed locations, maybe. So the idea is, if I have like an indirect branch, can I try to make sure that this branch is gonna go to places that I can tell it that is safe somehow? So am I like able to, I don't know, compute a CFG or something and enforce this to the process somehow? So like I said, this path layer basically like this is the concept of control flow integrity. So in general, so this is what control flow integrity is. Whenever you have like an indirect branch, you're gonna make sure that this indirect branch is gonna go for something a known path that you know is supposed to be safe. So these paths are basically defined by the application's control flow graph, right? So you can compute a control flow graph from the application, and based on this CFG, you can basically like try to enforce that branches which are not like foreseen in the CFG are considered illegal. So like I said, those which are not like predicted are considered like a violation to the control flow integrity policy. And there are some relevant questions to these, right? So how can we compute the CFG in the presence of pointers, right? So if you have like done the proper compilers subject already, you know that points to analysis is kind of like something incomplete. You are not like able to compute all the possible targets for a function pointer precisely in a static manner. So it's kind of hard to know where a function pointer is going to go. And but even if you are able to do this, how do we enforce this policy, right? So it needs to be something fast. It needs to be something efficient. Otherwise, you're going to like queue the process performance. So one idea that was basically the first implemented idea was like, well, basically you might be able to enforce the indirect branch to the first instruction of every function, right? So now instead of like allowing people to jump into the middle of functions, we are basically making sure that all the branches are going to the very first instruction of a function always. And this seemed to be a good idea, but in practice, people did show that this was not sufficient. So you were still like able to run a lot of malicious behaviors just by being able to call a different function, even though you were calling it from the start. And that's basically because some full functions can still be used out of context to achieve malicious computation. So imagine that in your, I'm gonna be talking like right now about the kernel context. So in kernel, we have like a bunch of features that are basically, they're used to disable security features because sometimes you're running whatever inside the kernel and you need that security feature to be disabled just to run an operation. I don't know, like get a new module to run, a new driver or something, and you need to disable that like momentarily. So you need these functions available. But if you're able to call these functions out of context, you might be able to disable that specific feature forever. And now that security feature is disabled, you might be able to launch a second attack and then like get the malicious behavior that you want to achieve by your attack. So also, for example, add user functions or like escalate privilege functions and things like this sometimes writes to a file function. So yeah, these sometimes, even though you are calling these functions from your very first instruction, you still like, this is still like very dangerous. I mean, does not like fully close the problem. So there was like a different idea, which is basically consists in like using prototypes, or prototype matching is how we call it. So if you ever declared a function pointer in C, you know that function pointers, they have like a prototype. Whenever you're declaring them, you're specifying the prototype for that function pointer. As you may know, functions also have a prototype, right? So whenever you're defining a function, it has like a return type and the arguments and the types for the arguments. And the idea is that maybe we can enforce the indirect branch to the first instruction of those functions that have a matching prototype. So if you have like a function pointer of a specific type, you can only invoke functions that have that very same prototype through that function, right? And this is what we call fine-grained CFI, and this is way more efficient than the coarse-grained CFI. To be transparent, there are attacks against fine-grained CFI which were like successful. So this is not like the silver bullet, but it makes it like much harder for attackers to exploit whatever you have running under this policy. So there are many different ways of enforcing the policy. There are like dynamic things, but I'll focus mostly on compiler emitted static checks, because this is the most efficient in terms of performance solution, and it's like what most of the CFI users out there are using these days. I'm not aware about any other scheme that's being used right now. So imagine now, like I'm gonna switch from pseudo C to pseudo assembly. imagine you have like this function foo here, and you want to invoke that function bar there, and the key here is the function, the indirect call, right? So the function pointer is inside the register R11, and all these instructions before the call are the CFI checks. So first thing we're going to do is that we are going to run a comparison of a very specific hash. So this hash is computed out of the function prototype. So you have like the function pointer prototype. You just like get that computer hash during compilation time, and then you emit this deadbeef here, which is the hash which is going to be compared. And then you're going to dereference the address that you were going to call and check if a few bytes before that address you have like a watermark which matches what you were expecting, right? So just to take a few steps back here to explain this a little bit better, when you were compiling this code, when you were compiling foo and you were compiling bar, you are able to compute a hash out of the function prototype, which is the first immediate of the CMP instruction here, the deadbeef. And whenever you are compiling the bar function, you are able to take the functions prototype and compute a hash out of that, which because the prototypes match, because they're like the same prototype, they will match whenever you compare them. So you just put a watermark before the function with the value there, which is deadbeef again. So if these two things do not match, the jump on equal that we have like right next, it's not gonna jump, right? So it's gonna be a not branch kind of branch, and the UD2 instruction is gonna execute. The UD2 is undefined behavior, so it's basically gonna trap the CPU. Otherwise, if these two match, the jump is taken, and you go to the call instruction, and then you go to the function. I know we're supposed to have questions in the end, but I would like to make sure everybody understands the concepts up until now. Should I repeat these or something? I'm taking the silence as no. So should I continue? Okay. I'll continue then. Let me go back to the slides here. So now let's talk a little bit about this in the kernel context, right? So this works in theory, looks neat, but I mean, what about like porting this to an actual scenario, right? So in 2014, I was at Unicamp at the time. We started a project to verify the challenges in running the Linux kernel under CFI confinement. So at the time I was studying at Unicamp, I was a visiting scholar at Columbia University and working with, at the time I was at Columbia, I was working with a PhD student who eventually became a professor at Brown and with whom I continued to collaborate afterwards. So it was basically like a collaboration between the two universities. And we started like trying to get the kernel running with CFI. At the time, CFI was basically an idea, so it was basically like an academic paper with no actual implementation out there. And we built a prototype of CFI protected Linux kernel using Clang. So Clang or LLVM, we use this to instrument the Linux kernel and get it running. So if you want the details about the project, there's this presentation called Drop the ROP, which was published in Black Hat Asia in 2017. So just search for it. You're gonna get like all the details of what we implemented. And when we were like on the way to kind of like make this a thing, some stuff happened. So first of them is that there was a GRSecurity wrap, which is a proprietary CFI for Linux. It came out before we finished kCFI. And because of that, I mean, we kind of lost a little bit of the originality factor here. So it became a little bit harder for us to publish papers on this because the implementations, they were like both based on the previous paper, and I mean, it became like a little bit, kind of one looks like the other kind of thing. Also, in order of like getting this to be used in the kernel, I mean, Google at the time, Google was like a very influent company. So at the time, they were like pushing for a different CFI solution, which is Clang CFI. It like works with different instrumentation than what I just described. Instead of like using tags, they basically transform every indirect branch into a jump table. And this jump table basically will contain all the possible targets for that specific indirect branch. And if an attacker wants to call something that is not in the jump table, it's just like not possible. And also at the time, Intel announced a hardware CFI extension called CT. So CT is basically a hardware feature, so a hardware extension that allows you to have like a hardware enforced CFI, and because of that, it's like super fast. And spoiler alert, it's super awesome. But anyways, I mean, I'm not supposed to be talking good things about, because I mean, I'm able to, but I'm not supposed to be advertising Intel products, I guess. So theoretically, it's research that kind of like reached dead end for us, at least from the academic perspective. So I moved to different topics at the time. I finished my PhD, and eventually I joined SUSE, like the Linux distro, to work on live patching. And life was alright. I was not like looking at CFI again. I was like basically living through, right? And eventually I decided to leave SUSE. And when I went out to the market looking for a position, I got hired by Intel. And now at Intel, I started working on how to make CT, so the hardware thing, the hardware CFI thing, better, right? The world is like a small round place. So originally, like CT was a thing that I was like a little bit annoyed about, because I was doing research on software things, and then the hardware company comes out and like launches an awesome hardware way of doing the things that I was trying to do in software. So it's like, come on, I mean, you're ruining my research here. But now, I mean, I started working for Intel, and I got to work on CT, which is like really cool, and which I was able to do just because I did some CFI research before joining Intel. And yeah, I was just basically like looking at CT and say, yeah, I mean, how can I make like this better? And one of the soft spots of CT is that it has like this thing called IBT, which basically is the part of CT that handles CFI for indirect branches, like forward indirect branches. So CT has like two parts. It has a shadow stack, which basically handles the returns. So whenever you call a function, the CPU automatically puts the return address in the stack, but also on the shadow stack. Then if the return address is corrupted, whenever you are executing a return, the CPU is going to identify that the return address there is not like matching the return address at the shadow stack, so it's going to trap. But you also like have the part that handles indirect branches, so forward indirect branches, which are basically like indirect calls and indirect jumps. And this is coarse-grained. So this is like that thing that we talked earlier, that's like not sufficient to prevent all sorts of attacks. And the way that IBT, this specific part, works is that any indirect branch is required to land on a new instruction, which is called end branch. So now you have like functions tagged with end branch as their first instruction. So in every function prologue, you're going to have like an end branch. And now basically an indirect branch can target that very specific instruction. And because it's coarse-grained, there's like no distinction between functions, right? So an indirect branch could like go to any function. That's basically how IBT looks if you take a look at the binary compiled with it. So you just have like an indirect call, you have like an end branch instruction in the bar, and then this branch is basically allowed, doesn't matter what's going on. This branch, which would basically like go into the middle of the function, is not allowed anymore. But you're still like able to call functions, and specifically in the kernel context, for example, you could call the function disable IBT. And this basically will set the CPU to disable the IBT enforcement, and then you could run whatever attack you want to, including, I don't know, it could also like call a function add user and not even like need to disable IBT maybe. So when I started working for Intel, I started looking into a new hypothesis, and was basically, well, can I statically emitted checks make IBT fine-grained? So can I like combine compiler instrumentation with whatever is in hardware and make something fine-grained and maintain all the security and the performance benefits of the hardware extension? So the hardware is like, it's great because it's the hardware enforcing things, right? It's awesome. And also it have like performance benefits, because if things are happening within the CPU, it's like much faster. So can I maintain these things and also use the compiler to make it like fine grained. And the conclusion is this thing we eventually like called fine IBT for the lack of like a better name. This name is something I'm not very proud about, but anyways, it's like the fine grained IBT. And this is what fine IBT looks like in the assembly. So in the color side here, you're gonna like be calling a function bar. So IBT is making sure that every indirect call needs to go through an end branch instruction, and you're not like able to jump anywhere else, or basically like anchoring the control flow to the beginning of each function. And what we basically do is that before doing the indirect call, we that very same hash we computed for doing the comparison. Now instead of like comparing these things, what we do is that we move this hash into R10. So if you're familiar with the x86-64 ABI, R10 is a scratch register, which means the compiler assumes it's gonna be destroyed between function calls. So we're able to modify here without like needing to save its contents or things like this, because the whatever callee is not going to expect any value inside of it, and whenever the function returns, the caller will not expect R10 to have its values preserved, so we can basically clubber it. And so we basically like put that hash inside R10, and then the function bar is called, and whenever we start executing end branch, I mean, since we are not like able to skip to a different part of the function, we will need to go through this instructions after the end branch. The first one is going to be this sub. Right? What the sub instruction is going to do is that it's going to sub. Sorry, my daughter is crying a little bit. Anyways, so the sub instruction is going to execute, and what it's going to do is that it's going to like subtract the very same hash value from R10. And the result here is that, I mean, if R10 has the hash that we're expecting, the result of this operation is going to be 0, right? So what this basically means is that, and this is a wrong slide because this was supposed to be a JZ, not a JNZ, so I'm sorry. But what this means is that the branch here should be taken, and the control flow should go to the bar entry label right after it. Otherwise, if you had like a different content inside R10, the result of the sub operation would not be 0, so the branch would not be taken, and the UD2 instruction would be reached, and that's like a trap for the CPU. So again, just making sure this is a wrong slide. It's not supposed to be JNZ, it's supposed to be JZ there. And of course, if you have like because all of this is in the function prologue, if you have a direct call to the function bar, instead of like calling the very first instruction directly, we are going to skip this instrumentation whenever we're calling. Otherwise, we would like need to place a hash for direct calls too, and that's the kind of overhead that we don't want to go through. So yeah, basically this is like basically done by the compiler whenever it's like kind of emitting or linking the binaries. And when I basically finished the fine IBT research, is like basically 5 years after I was playing with kernel CFI and my PhD. So the Linux kernel community pushed back kCFI as a viable solution. So if you remember, Google was trying to push for it, but basically the kernel community said no, it's too invasive, it's not going to work in the kernel. And now the Linux community started like looking at kCFI again. You know, they're saying, yeah, it's like a much simpler way to implement this, so having tags is kind of like better. And on the other hand, I'm like now on the fine IBT side of things, so I'm trying to push for fine IBT. So there was like, you know, kind of a big mess there. And well, despite the benefits, fine IBT is still dependent on hardware extension, right? So I completely understand when somebody says, yeah, I mean, this is good, but it's not for everyone. So older CPUs won't have CFI just because there's something better for CPUs with IBT. No, it's not like the way to go, right? So you want to like make CFI available for most people possible. So this is basically the problem, right, behind FineIBT. So FineIBT is like this dependency is like its major drawback. On the other hand, I mean, there are like some cool features with FineIBT, especially if you compare it to kCFI. So first thing is that it doesn't depend on memory reads. So this makes like everything much faster, right? So if you remember, kCFI would basically dereference the function pointer and make a comparison with a hash, and that's like a memory read, right? With FineIBT, we don't do that. So you just like put an immediate inside the register, and then you subtract this immediate from the register. And that's just like operations with immediates and registers, so no memory values. And this like makes instrumentation supposedly faster. So, but not only faster. I mean, not having like memory reads has like other benefits. So it's like, let's say it's better in the perspective of the existence of side channel attacks. It allows you to have something that security community have been pushing for, which is called execute only memory. So where executable pages are not like non-writable, but they're also like non-readable. Because I mean, this wouldn't be compatible with kCFI because kCFI needs to dereference the watermark, which is inside code pages. So there are like a bunch of like nice features about not having memory reads. IBT, although it's coarse-grained and has like its flaws, it's a great feature for handling with speculative execution policies, because IBT holds the speculative execution whenever an indirect branch is going to instruction which is not an end branch. So this is actually like great feature for tackling side channels, side channel attacks. I mean, so what I'm basically saying is that if you have like an indirect branch, and if of course if you're familiar with side channel attacks, you have like an indirect branch. And if you train that specific indirect branch to go somewhere that you want to have like loaded in your cache, so then you can leak it. Now this place that you were training the branch to go to will need to have like an end branch instruction. Otherwise, those instructions won't be executed, and nothing's going to be loaded into your cache. So the attack's not going to be successful. So with FineIBT, we can like inherit this from IBT. So it's really nice from the mitigating speculative side channel kind of thing. It's not like a bulletproof again, but it like helps a lot. And because it doesn't have like memory reads, it's probably like much better in the terms of performance. So we are running benchmarks for everything right now. So I'll say in a few minutes, but FineIBT is just like got merged, and or is about to be merged. And with this, we finally came to a final implementation for it. So we're now like in the point where we want to like do an actual performance validation or evaluation and compare it with kCFI. Yeah, but I mean, still there's like the problem, right? So FineIBT is hardware dependent. Okay, yeah, that's a problem. How do we handle this? So the kernel, for those of you who are not familiar with alternatives inside the kernel, it has like a self-modification mechanism. And this thing kind of like basically patches the kernel during runtime, depending on certain hardware features being available. So imagine that you are booting your kernel and you have like a nice instruction that's going to handle string operations, for example. But this instruction is not available in all CPU. So what the kernel will do is that the kernel will have like many different implementations for like a string manipulation kind of function. Then during the boot time, the kernel is going to patch itself and make sure that whenever this function needs to be invoked, the version that's going to be invoked is of the function that actually has like the better is a better fit for your underlying CPU. So if you have that instruction available, you're going to use a version of the function. If you don't have like that instruction available, then the CPU will patch itself and use a generic but slower version of that very specific function. So it's like a very cool kernel feature. It's like super complicated, looks like kind of dirty whenever you start like going through it, but it's like really nice because it allows you to have like the same kernel compiled for many different CPUs and have like the best performance or best available use of the features considering the CPU which that kernel will be running on, right? So it's like a distribution kind of feature that makes it distributing and having the best performance kind of easy. So somebody came up with this idea, which is basically, well, if the compiler, we can get the compiler to emit the kernel with kCFI, so which is like the software version of things. And during the boot time, we just check the CPU and see if the CPU has IBT available. That being the case, we can just like do the self-patching scheme and replace kCFI with find IBT, which is like really awesome because now you can have the kernel with kCFI for everyone that cares about CFI but doesn't have the CPU. But if you do have like the CPU with IBT available, you can just patch it and have find IBT, which will provide you all those nice features that I discussed about in the previous slide. So I want to give credits to about this idea to Peter Zustra. So Peter Zustra is a kernel engineer. He's also working for Intel. He's a brilliant guy. Big fan of him. And he came up with this idea, which basically like made all these things come together and brought peace to a lot of people who were discussing what would be the best solution for getting kernel CFI. So it was like really a nice move. So what's the status now? I wrote this in 21 of October, so it might be a little bit outdated. So kCFI patches, they were like kind of rewritten by Google, and they were sent and merged to upstream. I think in October 3rd. I mean it's already there. If you clone the Linux trunk, you're gonna see that this is already there. You're gonna need like latest Clang, right? So it's dependent on Clang for compiling the kernel, but it's already there. It supports everything, and it's like really nice. FindIBT support has candidate patch sent, and it may merge soon. So there were like a few developments on this. So the first candidate, there were like some discussions about it. Then there was like a second version. All of these written by Peter Zustra, so he's the one like taking care of upstreaming FindIBT. There was like a second version, and the second version got accepted. I know that recently it was moved to the tip 3 and should be merged into the trunk really soon. If it was not already merged, I mean I haven't looked like lately, but I mean it's not like a candidate patch anymore. It's like people know the actual implementation of how this is gonna go. And well, now everyone should get their best available CFI scheme. So hopefully the Linux kernel is going to be more resilient against control flow hijacking attacks. And yeah, of course, I'm like super happy about it because I mean, this is things I have been working since 2014. So it's been what, 8 years since I first touched kernel code with the intent of like getting CFI to it. So yeah, I'm like super happy about the results here. Also, big thank you to Sandro for supporting this research. I know that at the time he was like a little bit kind of annoyed because he was not like a very experienced with security, but he has like this crazy PhD student willing to do security work that was like kind of related to compilers. So he embraced like advising me, and this support was like very meaningful for all of this to happen. So I'm really like grateful, you know, that I had Sandro as my advisor during my PhD days. Some personal takeaways here. Short-term research goals are overrated. You know, you need to do things because you believe in and because you want to contribute. So research is meant to improve the world around you and not to increment your published papers list. I know I'm not supposed to be saying this to a bunch of like PhD students who are like kind of crazy to publish, and you kind of like need that because that's a benchmark for how well you did in your PhD. But my experience basically told me that sometimes it's going to be better to do a meaningful work, even if you are going to publish in like a non-academic conference like I did in Black Hat. Sometimes it's going to be better because I mean if the work is really relevant, if it's something that really matters, people will look at it. There's going to be turnarounds, and that's basically how we contribute. I mean, that's my perspective, of course. That's my experience. So When I left my PhD, I was like a little bit disappointed with my track record for publications and things like this. But in the end, it turned out to be great, I guess, or at least enough, because doing that very one presentation at Black Hat Asia is basically what got me through until I got to Intel and continued to work on CFI. So I think that sometimes it's better to benchmark things by how relevant you think they are instead of like how many papers you're going to get out of it. Another thing is like there shouldn't be size in research, right? So we're not like talking about football teams here. So I mean, in first place, I was like doing kCFI, and eventually I was like kind of doing fine IBT and seeing people pushing for kCFI have a different opinion than what I had, and sometimes it feels like you were just discussing with other researchers and trying to push that your solution is better for these and for that, and that maybe you want to like sell things, but that's basically not how things should be, I think. So I mean, every problem is a problem. There are like many perspectives to every problem, and as a researcher, I think that our goal is like to find the best solution available, so we can make things better and not like make things better for us only. You know, I mean, I know like credit is something that we want to get for our research, but sometimes we're like on the wrong end of things. Sometimes we're just like doing something and there's going to be a better solution out there, and we need to acknowledge that. Yeah, I mean, I explored this specific scenario. I mean, just because you went to a dead end, it doesn't mean that your research is worse or anything like that. So in the end, all of these things get together and compose for like a bigger end. So yeah, don't look at other researchers doing similar things, but with a different path that they're like your enemies. That's not the case. So everybody should be really working together. And final takeaway is have fun. I wouldn't have like done any of this if it was like kind of boring. So whenever you're picking a topic, pick something you have fun doing. Pick something that you find challenging and that excites you. And I really mean it. I mean, you at least my experience. I mean, there's like just so much sweat and blood doing kernel and compilers, which are like two super complicated things. So if you don't have fun doing it, perhaps you should like looking into doing something else that might give you fun, because in the moment you start like getting deep into things, it's going to require you know, sacrifice and energy and a lot of commitment. So this is like the most important part of it all. If you're not like having fun, you're not going to be able to go through very much. With that, I end my slides and I open for questions, and I hope nobody is left. I cannot look at you and not throw things at you to wake you up. So I hope you are still all there.
Thank you, João, very much for your presentation. And yeah, this was a very interesting tale. I've been part of it for some time, and I know how hard it was to put everything out there. So congratulations for the fine work, for sure.
Thank you.
Okay, I am open for questions. Anybody?
Two questions. Hi, João.
Hey, Kai.
Glad that everything has worked out for you.
Thank you.
Very nice that. And two small questions. So the move instruction and the sub instruction, they are put there by the compiler.
Yes.
Okay. And another thing that wasn't clear is if the fine-grained IBT prevents code reuse.
Okay,
because
so go ahead. Sorry.
No, it's okay. It doesn't look like that. If you try to reuse the code for the attack, it prevents it.
Okay, yeah, let me go back to the slide and go through it again. So the original idea of FineIBT was like kind of having this emitted by the compiler, just like you asked, right? So this is like basically the code that the compiler emits.
Mhm.
But the way it ended up like in the kernel, is that this is actually like emitted by the kernel itself. So when it's like kind of self-patching. So the way it works in the kernel is the kernel will emit, the compiler will emit the kernel code with kCFI, right? So the other instrumentation, the one that does the CMP. And during the boot time, if the kernel identifies that your CPU has IBT, then it's going to patch these instructions on top of the other instructions. It's going to replace one by the other one during runtime. So when I said that the compiler emits this, I meant the original way we thought about this, but the way that it was like implemented in the end is a little bit different. Now,
okay, that part, I mean code reuse attacks,
yeah,
like
sure.
you reusing functions.
Yeah, sure. I'm just like going explaining that you're answering your first
Okay,
question
okay.
again. Yeah, because I did not like go completely about it. Now it's answered. So how does this basically prevents code reuse attacks, right? So you have like this two hashes here, right? Like that beef and that beef on the left side and on the right side, right? And
Yep.
like I told you, the call in the left side, it needs to, I mean, whenever you're writing this in C, you are using a function pointer, right? And this function pointer is going to have a prototype, right?
Mhm.
And this prototype is what's going to be used to compute that beef word which is used in the move instruction. Okay, so that's where that beef came from. And
Okay.
whenever you are compiling a function, you look at the function prototype, and using the function prototype, you emit the word which is used as an immediate in the sub instruction. So the write that beef now, it's just there because it's computed out of the bar function prototype. So if you have a different function, let's say you have like a function disable IBT, for example, that function is going to have like a different prototype than bar, right? So they don't have like the very same prototype. And because of that, the function disable IBT is going to have a different word. So the sub instruction in the prologue of the disable IBT function is going to be sub R10 and a different immediate there. So
Yeah, okay.
if you're calling disable IBT for the pointer on the left, the word that's going to be inside R10 is going to be that biff, and it's not going to match the word which is in the disable IBT function, right? So because this is a mismatch, the instruction, the JZ, which should be the next instruction, should like not be taken, and then the UD2 instruction would be executed. Does it make sense?
No, yeah, no, 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 it was clear.
Okay,
Thanks.
cool. Yeah, sure.
Thank you.
Uh, let me go to the chat again. I heard a beep. Somebody sent something.
Any more questions, Kyle?
No, no, for me
Oh,
it's
okay.
fine.
So
Thanks.
Pedro, please.
Yeah. My question is, do all of these strategies have impact in performance? And if so, have them been measured? And like for some applications, we really like embedded stuff, things that aren't connected to the internet. We really don't want to sacrifice anything, right? So can these things be also turned off if the impact is too strong?
Can they be what? Sorry.
Turned off.
Oh, turned off. Okay. Yeah. So okay. Performance. Okay. So kCFI, I measured performance of that when I was still at a PhD. So if you take a look at the drop presentation from Black Hat Asia, you can find the numbers there. It's, if I recall correctly, it was something around 1 or 2% for macro benchmarks, a little bit bigger than that for micro benchmarks, kernel micro benchmarks. So I don't recall the numbers on top of my head, but yeah, I remember that was something that was like kind of worth to pay for. For fine IBT, we did not measure it yet because we were still like waiting for the final version of it that would go into the kernel. So whenever we do a comparison between the two, we have like the actual final implementation. And it just got in, so like I think last week or something, so this week even. And now is when I'll start like running these numbers. Actually, there's someone else in my team who's gonna like run the numbers. But I mean, it's we're gonna run the numbers now, and we might be able to compare this. So the expectancy is that performance won't be bad because first kCFI performance was not bad at first, so it's already like 1 to 2% something. And we expect FineIBT to be faster than kCFI because there's no memory reads, right? So because you don't have like a memory read, there's not going to be a lot of impact in your cache. There's not going to be any sort of like strong contention or things like this. So we expect this to be much faster. I mean, if you're familiar with instruction kind of performance or throughput, you know that instructions that only have like immediate and registers are like much faster to execute than those that depend on the memory read. So we really expect it to be faster than kCFI. But let's see. I mean, we did not run the numbers yet. And turning off is something that I think you might be able to do because I mean the kernel is able to patch itself, right? So you might be able to patch this sort of like instrumentations during runtime. I think that it's something. It's gonna be like turning it off. It's going to be an expensive operation because I mean you need to make executable pages writable. That's definitely gonna cause TLB flush in your operating system, and then you're going to need to write, right? So you're going to need to replace the instrumentation with knobs, and then you're going to need to flip the page back into executable. So that's the only way I could see this being turned off. There could be a different, smarter way of instrumenting this that could make it turned off. Actually the way let me show you a different slide here because I think it's very relevant to the question you made. Let me just drop because it's a slide from a different presentation I made in the Linux Security Summit.
João, do you think that this is going to be turned on by default in the newer kernels?
I think so. Yeah, I mean, I'm not sure how it's gonna go with distributions because distributions are like they're like their own wild beasts, right? So they take the kernel and modify it like very very deeply. So sometimes they're gonna have like even their own modules that might not be compliant, and because of that, they might want to disable it. But I think that the idea in the trunk is that the to always like kind of have it like enabled by default. I mean, especially with FineIBT because it's like it adds a little bit to side channel kind of mitigation, and it like allows you to replace red poolings, for example, and red poolings are like super expensive. So I think that this is like a reason why the kernel community is like kind of excited about it. So I think so. I think it's going to be default. Yeah.
Okay.
So actually, the slides I was gonna show Pedro, I'm not finding those. But anyway, I mean, the way I see it, like being turned off, is just like by patching the binary. There could be a different kind of instrumentation that could make it possible. I presented in Linux Security Summit 2021, I think, and there I discussed a way to disable it like during runtime, but the instrumentation would still need to be in place. It's just like a way to disabling the policy enforcement. So if I have like a mismatching hash, it just like would not like trap the CPU. Instead of that, it was like bypass things under certain scenarios. So the performance overhead would still like would still be present, which is I guess not what you wanted. Right? You were looking into getting it faster, making it faster. So I think that final phrase for answer your questions that is still like needs to be researched. Maybe there's a way. Currently there's like no way. Even because I mean it's a security feature, right? And when it comes to security features, people really try to lock the features in a way that attackers might not be able to disable it. So yeah, I mean the answer is no. Right now, there's like no way to disable it, and following thought is perhaps it's an open topic for someone in the audience who might be willing to research it. So there could be developments out of that. It's a good master's degree research, I think.
Okay, thank you. I don't see any ranks raised anymore, so I have one quick question, João.
Sure.
Did anything change in the kernel that made the kCFI easier to implement now, or the change was just because they decided to drop Clang CFI?
I think let me see. I think that it was mostly, I mean, certainly the thing that changed that made it like much easier right now is having proper support for Clang. So when we were doing our research, so kernel was not like compatible
Yeah.
with Clang. So we had like to hack a lot to make it like even the vanilla kernel to be compiled with Clang. That was one thing. Another thing was like kind of getting the void function prototypes kind of like fixed. So it's like something just to give people an idea of what I'm talking about. So in C, you can have like a void star pointers, right, which basically can point anywhere, and that's actually like something that you can use to invoke functions. So I mean, a function can actually like have a void star parameter. I mean, the pointer can have like a void star parameter whenever you're declaring the function pointer, and then the function itself has a specific type for that argument, which is like in parity with a void star parameter. So now you have a situation where in C it's legal to call a function with an unmatching prototype, right? Just because the void star parameter basically means anything, it's allowed to call anything, right? So when we started like working on the kernel, we had like many of these scenarios, and because Clang CFI did develop itself, so I mean it was never like merged into the x86 tree, but it was merged for the ARM. So ARM had like support for Clang CFI for a while. It's been removed now to get kCFI in ARM, but it did run with Clang CFI for a long while, and because of that, I mean, I think that these void star prototypes started like getting fixed because they need to be fixed to a way that will work with CFI, and that also like made it like much easier to get things on right now. And in the end, I think that the thing that actually like matter a lot is political reasons, right? So at a certain point, people figured out that you cannot have like a pointer equivalence with Clang CFI because Clang CFI basically destroys function pointers in general. So now pointers, they're just like a value inside or like an index inside the jump table. They're not like the actual function address, and this would like ruin other kernel features and make it like harder for doing some of like the nasty tricks that kernel developers do. And they just said, yeah, I mean, this is not like something we can do. We need to look into something else. And that's when they started like looking at kCFI.
Yeah, they probably went that way because of performance, but they didn't realize that they would break something else, right?
Exactly. That was exactly the case. So kernel has like crazy features. I could go on into that, but I guess we don't have time for it. But I mean, there are features that would be broken, and that's the thing. I mean, kernel, they care about performance, but it was surprising to me from like an academic perspective that they don't care that much as academics do. So sometimes they're even like willing to take the less performant path. So let's implement it like in a way that's is not as fast as this one, because I mean the performance impact is not going to be that big, and the code's going to be more maintainable or more readable or something like that. We care a lot about this.
I think Hervé has one more question. Please, Hervé.
Yes, just a quick one. So thank you, João, for the presentation. It was really nice. Actually, I attended your PhD defense in that time, and it was really nice to have the following of the story.
Cool.
And my question is there any other constructor that provide hardware instruction for CFI also than Intel?
Yes, I mean ARM has something which is called BTI. So Intel has IBT, ARM has BTI. They work the same way. BTI is also coarse-grained. So it's like kind of same. I mean, I don't really know how it works to be fair. I never looked into it, but as far as I know, it's like gonna work same way. So if you have like an indirect branch, it needs to land on a specific instruction, and it's like coarse-grained, right? So every function is gonna have like the very same instruction, so you can go to the function prologue of whatever function you're going to. That's what I know about ARM. ARM also has like a different thing called pointer authentication that basically allows you to put a signature whenever you are assigning a function pointer. And this way, if an attacker corrupts memory and overwrites a pointer, he will need to know how to do the authentication kind of thing, and because it's done. I'm not like, I don't know about the details, but I think that there's something underneath the CPU that basically is used to sign the pointers, and because the guy doesn't know how to sign the pointers, he won't be able to make it point anywhere valid. I know that Power has something to. I think it's similar. It's in the line of pointer authentication too, but I'm not like aware about the details. What else? I know that RISC-V is looking into have something like IBT, but that is fine-grained. So I know about a company trying to do that for RISC-V. And yeah, these are like all I know about CFI, at least in terms of hardware perspective. Perhaps I'm forgetting another one, but yeah. So for pointer authentication, I know that macOS already runs with that. So M2 has support to that, and if you're running macOS, you have like pointer authentication in place. And there are like some other technologies which are also like going to be like really important in this memory corruption mitigation scenario. So Intel is like launching something called linear address masking, which is a good technique to make sure that whenever you're using a pointer, you're like making sure that you are pointing to a valid target or things like this. So if anyone's curious to what's going to come next, I strongly recommend looking at that, because that also helps with other kinds of attacks. So it's more like tackling the memory corruption problem and not like only the control flow hijacking, which is a consequence of memory corruption, right? So it's like going to the root of the problem with linear address masking.
Okay. One last question from Pedro. Please, Pedro.
Yeah, sorry if I'm taking too much time.
No, it's fine. I mean, with me, it's fine.
Yeah, my question is if fine ABT is architecture independent, right? Because it just you're just adding the hash to a register, right? So I wonder if that's done at LVM IR level instead of doing it separately for each architecture.
Okay, so it's not in the architecture independent because it depends on the IBT part of things. So let me show you the instrumentation again. So whenever you are doing this call, you need, I mean, you depend on the end branch instruction being there, right? So if the end branch instruction is not there, the CPU is gonna trap, right? And this is something that the IBT, which is part of CT, which is Intel tech for Tiger Lake and later CPUs. So you need this for this to work. Otherwise, even if you have like this very instrumentation in place, but the policy that requires an indirect call to land into an end branch instruction, if this is not in place, an attacker could just like corrupt the pointer and instead of like jumping to the end branch, jump directly to bar entry, right? And this like needing to land on end branch is what like really anchors the control flow to go through the checks that we are trying to do. So it's not like hardware independent because it depends on the end branch and on the CT kind of thing. On the other hand, the concept itself, it is kind of hardware independent if you have a way to enforce this sort of behavior. So with ARM BTI, for example, that I just explained, that it kind of like has like this very same kind of behavior. Basically, you can implement the very same thing. It would be architecture independent, yes. The only thing I know is that I think that it's not like so interesting for ARM because ARM BTI doesn't give you the side channel side channel benefits that IBT gives you. So it's only like the performance would be in game for them. And like I said before, I think that kernel people don't care that much about performance. So just to have like all the complexities needed to flip between kCFI and find IBT, which in this case would be find BTI, I guess. It's not like worth to get like a small performance benefits. So yeah, I mean it's a little bit architecture dependent, I would say. And then you asked about if it's implemented in the IR level, right? So no, it was implemented in the backend of the compiler, mostly because these things are like very tight to the way that the assembly is emitted. So it's kind of hard to generate this in the IR because then you're gonna have like lots of different.
The optimization would mess up with your
Exactly.
annotations, right?
Exactly. So
This needs to be post optimization.
exactly, it needs to be like by the very end of the pipeline. So I mean, even kCFI, when Google re-implemented it, they tried to implement this in the IR level because they wanted it for ARM too. But I mean, the kernel devs, they just looked at whatever was being generated and said, I mean, this is like too messy. We want like this very same snippet every time. Because then in the back end, all the instrumentation they were generating was like kind of being moved around and the structures were being changed and all that. And the kernel dev said, no, I mean, we need something kind of fixed in the very same place always. Because I mean, if we want to flip this for something else, if we want like kind of self-patch this somehow, we need this to follow like a similar pattern always, so it's more like maintainable. So Google had to come with a newer version of kCFI that now implemented this specifically on the backend. So now you have like a x86 backend and ARM backend implementing kCFI.
Very nice.
My other question was exactly that, if it's implemented for ARM too.
kCFI, yes.
Yeah. And how about RISC-V and other things?
So RISC-V is like pretty kind of new thing, right? So I'm not like 100% aware about what's going on there. I have some contacts, some peers that work in RISC-V companies, and what they told me is that I mean they're like kind of looking on having something in hardware for doing fine-grained CFI, but honestly I'm not aware about the progress. I don't even think they would tell me because it's research, right? So they want like get the patents first before letting somebody at Intel know about it. So yeah, I don't really know, to be fair, and but I know that they are interested in this. So
But do you think that the kCFI solution will run in RISC-V?
I think so. Yeah, I think that kCFI is quite like hardware. Yes, it doesn't depend. I mean, it just depends on like some really basic instructions. So like if you are able to reference memory and do a CMP, then you might be able to have it like running in your architecture. The thing is, as far as I know, Google only cares about x86 and ARM. I don't know. I mean, maybe they do care about other stuff, so I don't really know. But these are like the two major platforms that they use. So ARM because of the mobile stuff,
Yeah.
and x86 because of data centers. So that's, as far as I know, that's why they were like most interested in these two backends. But I don't know about the rest.
Okay.
All right, thank you.
Thank you, Pedro. Oh, I think we can thank João for the presentation and the discussion. Very instructive. Thank you, João. Congratulations on the work.
Sure. Yeah. Thank you again
Thank you.
for having me. It's really nice to talk to you. I mean, whenever you need somebody to fill a gap again, just send me a mail. I'll be happy to be around. With Intel, there's like always, kind of some bureaucratic work that needs to be done for me to be able to present. But if you let me know with a little bit of time, I can work that out, and it will be a pleasure to talk to Unicum people. Again, thank you for all the hard work we've done over the years, Sandro. It was it's especially good and happy for me to be here talking.
Looking
to
back now, it was fun, right? At the
Exactly.
time, it doesn't look like that, but now it was fun.
exactly, and like worth it. I mean, all the effort paid off for sure. So it's really thank you for like having me and like embracing this crazy student that wanted to do something out of his mind or something.
It was a pleasure. It was very fun, for sure. Hervé, I think we can stop the record.